All right, Steve, we talked about problems. You're getting called out. You took us through the building envelope when you first get there to assess how big of an issue is really going on. Now take us to the occupied space. When people are looking at floor by floors, get into there and let's talk about that and the problems.
You bet, Dave. Let's go back to that 5-story. So after walking in, feeling the lobby, going up and identifying the air handler that's providing the air, this air handler happened to be on the roof. So this is a built-up system feeding multiple floors. And it was kind of troublesome when I saw that we had low airflow and low static pressure on the floor closest to the air handler. Not uncommon, but this was a big indication that we have some problems here. When I first walk into an occupied space or the office areas that we know, one thing I like to do is basically, listen for extreme velocities, detect any odors, notice if there's any pressure changes when you go in and out of the elevators, as we just discussed, and just look for the obvious. I talk to the engineer. I ask him, hey, do you get repeat calls to certain areas on the floor? Do you have a west side problem? Do you have an east side problem? All based on the sun's angle and time of year. Does your building lose static pressure as the day progresses? Do you have to start the building very early in the morning to meet pull down load, which is pretty common in the industry, especially in the warmer seasons. So we look at the basics and try to get a sense of what's going on for the occupant, for the tenant themselves. I go to the air handler and we'll lay hands on the air handler. I'm not saying putting your hands into the rotating assembly.
Well, you have been called the building whisperer, so
we do lay hands on. And it's true though. You got to know your equipment.
Yeah.
If you feel vibrations coming from an air handler, there's different critical harmonics at different RPM. Again, the merchant marine engineering background told me that if you're feeling multiple frequencies and vibration levels, you're either running way out of design spec or you've got mechanical failure that's imminent.
So let's separate the two systems. So that this one was a built-up system, meaning the units were on the roof,
Mm-hmm.
and then they had ductwork run from the roof through the 5 floors, and it tapped off.
Mm-hmm.
Some buildings will have what they call a floor-by-floor system. The floor have its own fan room, where you could go in and be doing this. So they could be either or.
Correct.
It's on there.
Correct. And it's funny, there's two different design theories behind both. When you have a floor-by-floor system, you're not stuck with one air handler failing and you lose the whole building.
Yeah.
But a lot of times buildings were built, it was more convenient to put all the big equipment on the roof and run a main air shaft down through the core of the building. The other part of these systems is with floor-by-floor systems, you're very limited on the amount of fresh air that you can get in to the building. You have an outside air fan that's mounted on the roof generally. It's pumping air down into each air handler room, but it's a very small duct and it better be working very efficiently. The big built-up systems, you have economizer dampers, you have big outside air intakes, filter banks. No problem getting outside air into the building generally. Back to the floor-by-floor systems, when they were assembled, they were thought of as low static pressure systems. So the attention to sealing them and the amount of duct sealant, it wasn't as critical because they're only expected to operate at 2 inches or 3 inches of static pressure. Big built-up systems, up at the fan, at the big van axial fans or large centrifugal fans, you can have up to 4 to 5 inches of static pressure. So they were a little more sensitive when they assembled these ducts that, hey, we're going to put sealant on them, we're going to pay attention to how
we might be talking 100, 200 horse motor, the built-up systems. We might be talking like a
15 to 20
25 or something like that horse motor on there. So big difference.
Big difference in design theory. Round duct versus rectangular duct, for instance. Rectangular duct has a propensity to leak. More surface area that can cause deflection from static pressure. Building controls that have gone crazy over the years and dampers that didn't coordinate and open. I've seen systems that were ruptured because the van axial fans had overpressurized the main trunk. So there's areas when we're in the occupied space, we take all this into account. When I look at, for instance, dust loading and particles, this is huge in the building operation. Filters are taken for granted generally, but air filters are critical in maintaining the cleanliness of the equipment, so you get your proper heat transfer and you don't foul the ductwork. But it's also to protect the occupants. Particles that carry through the system can also carry odors, can carry pathogens, and can make housekeeping a real problem. We go out and when I assess a facility, I look at air velocities coming from air registers. We take particle counts to read what's actually being delivered to the occupant. Somebody might complain to you and say, hey, every time I come to work, I start sneezing. You need to change your air filters. And we know that the engineers have changed the air filters. There's dates on the filters. There's readings taken. But you don't know what you're delivering until you take a particle counter and measure what is coming out of that air register versus the outside air versus what you have in the common areas at the filter bank. There's many readings that we can take because, again, we're dealing with something that's invisible. But we have a way to capture and quantify all the parameters that you're providing to that occupied space. So it brings us into a unique area that we're almost like the Ghostbusters. And I feel that way when I've got a particle counter up next to an air register, or I'm using an infrared camera to look for thermal stratification. That's when you don't get a good temperature exchange in the occupied room, and you'll see temperature gradients in that room. And so you can really diagnose what's happening for the occupants. A lot of times I can pinpoint zone issues for the engineer prior to performing any real repair or remediation activity.
Yeah. I know part of it too is you can go right to the unit, and the first couple of things you can do is if it has a drive, which most of them do, you can see is that drive maxed out. What is it running at? It's a 60 hertz drive. Is it running at 60? Is it running up in the upper 50s? I know if you see something like that, you know that fan is having to work harder, and that's kind of telling you that we probably have duct leakage or veins or dampers that are closed. It's something impinging, something keeping the air from delivering out there. I know part of the other tools that you use too is you'll do how fast is the fan, what's the velocity, what's the static, and those are things telling you if the design was say 350 and you're getting 500. Okay, I know there's a problem out in the system.
Right.
So those are things that you also do when you look at that conditioned space.
The velocities, I'm glad you brought that up because the velocities are critical not only for your filters to capture the particles the way they're designed to, because certain filters use high velocity air, they're impact filters. Other filters are made for variable systems like our VFD systems. But it's also that coil velocity. What's the air going across the cooling coil? There's a design flow rate on every mechanical schedule for buildings, and it's generally the 400 to 500 feet per minute across that cooling coil. If you're overblowing that coil, you get a diminished cooling effect, and you also don't get enthalpy control. You can't control the moisture in the air. Part of air conditioning is the conditioning part, and that's humidity control. We don't like it when it's above about 42% relative humidity. And our bodies don't like it when we're below about 35% relative humidity. If you've ever walked into a building and it kind of had that swamp smell to it, that's generally an air handler that's not controlling the enthalpy or humidity on that floor. Part of that too is that when you have these design velocities that are overblowing the coil, that you're over-designed, you're also having to overpump and run too many chillers. So everything you're doing at that fan is affecting the largest prime movers or electrical consumers in your facility, which is the chillers. So it's almost like you've got a brand new 500 horsepower engine, but you've got a slipping clutch and you've got bald tires. Well, you're going to make a lot of noise, but you're not going to get down the road like you're supposed to.
Okay, so just to kind of recap, so if somebody, when you come out, you're doing your assessment, if a building engineer is there, or a property manager or the owner, whoever's on there, and they notice things like, boy, the fan's really loud. Well, I look at the drive and it's pushing 60. I notice people are complaining, cold calls, hot calls. You notice some people wearing sweatshirts again, some wearing tank top, which we've seen that before in buildings, which is really funny on the same floor. It was hard to believe, but when you start, when if I'm an engineer, even being there, if I'm seeing that, I know I've got a problem. But these are things that we see, and we know exactly what to do from there
Correct.
on there. And I think what I like to do now is, we've talked about the problems, we've talked about the envelope, and we've talked about now the occupied space on the floors. Let's talk about, let's take a second, let's talk about the solution. Because there is a solution, especially in this day and age where everybody's worried about disease and healthy air environments and stuff like that. There is a solution. And we'll just take in a few minutes, we'll go ahead and we'll talk about that.